This is an optimization problem. You know it is because you're trying to find the biggest or the smallest of something. In this case, we're trying to find the least expensive such container. Whenever you do these problems, there's a few steps to follow, and they're almost always going to fall into this pattern in some sort of way. So the first thing you want to do is you want to identify your variables. A lot of times this comes with drawing a picture of some sort. You want to identify your variables. You want to find the function to be optimized. So what that means is you want to find a function for the thing that you're trying to make the biggest or the smallest. And you want to find that function in terms of the variables that you've identified. So in this problem, what's the thing we're trying to optimize? Well, find the word biggest or smallest or least, and we have the least expensive such container. And so what are we trying to optimize? We're trying to optimize the cost, the least expensive such container. And then you want to find a relationship between the variables. Usually, or not usually, but often, this is going to be a formula. And if it's something geometric, it'll be a geometric formula. So find a relationship between variables. And when you do that, you're going to solve for one variable in terms of the other. Once you have solved for one variable in terms of the other, you're going to plug that variable in to the function you're trying to maximize or minimize. Now you should have a function. If you only had two variables, you'll now have a function in one variable, and you are ready to find the critical points of that. And you do that by you take the first derivative. So you take the derivative, and the derivative, you'll set it equal to 0, and that will identify possible points that would give you where the function has a max or a min. So you take the derivative, you set equal to 0, and you solve, and then you test those points and your end points, like the biggest or smallest points that are possible in your scenario. So test those points and your boundary points, if you know what those are, to determine max or min values. Okay, so in this instance, to identify the variables, a lot of times you'll want to draw a picture if it's geometric. So we have a rectangular storage container without a lid. So here's our storage container, and we have the base is included, and the sides are included, but not the top. So we have, draw it in black on a black screen. So we have the sides are included, and the base, but not the top. And each of those has a cost associated with it. So we have a length, we have a width, and we have a height. And so if we want to look at the cost of this thing, the cost is going to be the cost for each of the sides and the base. So let's look at the sides. So the area of this front here, outline the front, the area of the front is the same as the area of the back. And so those are going to have, they'll look like this. They'll have the length and the height. So that'll be the area will equal the length times the height. And I have two of those. So the front is length times height. The back is length times height. Now let's look at the sides. So the sides are width times height. So the two sides, so I'll just say side 1 is width times height and side 2 is width times height. And now how about the base? The base is the bottom part, and that's the length times the width. Okay, so we have that, so we have the area of each of the sides in the base. We know the base costs $20 per square meter. So the cost for the base is 20 LW. And the material for the sides is $12 per square meter. So cost sides will be $12 times the area of all the sides. Well, I have the front, and I have the back, and I have one side, and I have the other side. Or I have 12 times 2LH plus 2WH. Okay, so now I'm ready to have my variables were length, width, and height. Those were my variables. My function to be minimized is my cost function. And my cost is 20 LW plus 24 LH plus 24 WH. Now I want to look for a relationship between the variables. Well, I actually have three variables here, so I'll need two relationships. So one relationship is that the length is twice the width. So I have the length equals twice the width. The other relationship I have is going to be the other piece of information you have in the problem. The other piece of information I have in the problem is that the volume is supposed to be 10 meters cubed. And so the volume is 10, and that is length times width times height. So what can I do with this? Well, I know that the length is 2W, so I've got that. And so now I can say 10 equals L. W is, L is 2W. So 10 is L is 2W times W times H. So 10 equals 2W squared H. So that means H equals 10 over 2W squared. Alright, now let's go back to our cost function and we can plug in everything in terms of W. So cost equals 20, I'm going to rewrite it, 20 LW plus 24 LH plus 24 WH. Okay, so that would be 20 times L is 2W times W plus 24 times L is 2W and H is 10 over 2W squared plus 24, W is just W, and H is 10 over 2W squared. So this is 40W squared plus, let's see, this 2 can cancel with that 2, and I get 24 times 10, 240, W over W squared is 240 over W, plus that can cancel, I'll cancel that, so I get 120 over W, so I get 40W squared plus 360 w to the negative 1 is my cost in terms of w. So now I have a cost function all in terms of one variable. So now I take the derivative. So the derivative will be 80w minus 360w to the negative 2, and I set that equal to 0. So 80w minus 360 over w squared equals 0, or 80w equals 360 over w squared, or w to the third equals 360 over 80, or w to the third equals, what was that, 9 over 2? Or w equals the cubed root of 9 halves, which is going to be some number. Let's see, that will be 4.5 raised to the 1/3. I get w equals 1.65096, and then what's the question asked for? The cost, let's see, find the cost of materials. So I would need to now take this number right here and plug it into my cost function. So I would plug it into this function right here. So I would say my answer is going to be 40 times the cubed root of 9 halves squared plus 360 over the cubed root of 9 halves, whatever that is, if I didn't make any mistakes. Now, I did not prove that this was the least expensive container. But you could check, like, if you wanted to check your boundary points, you could say, well, what if my, it's hard to figure out what that would be. So I'm just going to leave it like that for now and assume that I have the right answer. And if not, you can just not.